Alright, so question number 1, we have a uniform ladder of mass m and length L rests against a smooth wall at an angle theta naught as shown in the figure. What is the torque due to the weight of the ladder about its base? Alright, so the first thing we have to do is kind of clue in on these code words that they're using. So we want to know something about the ladder about its base. So that means they want us to treat the base as the pivot point. So we're going to say we are pivoting around the base of the ladder right over here. Everything is going to pivot around there. So that's our pivot point, which is important because when we were using torque before, we said our torque is equal to the distance from the pivot point times the force that's acting perpendicular to our object. So this R stands for the distance from the pivot point. So yeah, we have a torque that's acting from this wall over here. That's going to push us this way, but we don't really care about that force or that torque. We want to know the torque from the weight, so the torque due to the weight of the ladder. So what we need to say is we need to identify where that weight force is acting in relation to the pivot point. So we said that objects have uniform objects, and really all objects have this spot where we can say, hey, this is where we can pretend that all of the mass is concentrated around. This is our center of mass, which is where our weight force acts. So when we were doing things with meter sticks or rulers, we said that that center of mass is directly in the middle. That's where we can balance it. That's where that weight force is acting. So the same thing is true of this ladder. This ladder has a length of L, which means that our weight force is acting at L over 2, halfway. So we have this weight force, this force of gravity, acting halfway at this distance, L over 2, from our axis of rotation. So if I'm going to write this out, torque equals our distance is L over 2 times the force. And we know it's this force of gravity, but it has to be this perpendicular component of gravity. That's a terrible perpendicular. There we go. So this perpendicular component of gravity. So what we need to do is say, well, this gravity, this force of gravity, this weight force, is acting downwards, and we can split it into components. So we can have a component that is perpendicular, so I'm going to call this FG perpendicular, to my ladder, and then a component that is parallel, FG parallel to the ladder. And I'm going to rewrite this so it's a little bit more clear. This is FG. So we have a spot that is parallel and a part that is perpendicular, and we care about this perpendicular piece. So what we have to do is then just kind of identify where the angle is and do some trig, and that's really difficult for me. So I'm going to draw a little picture down here to help me out. I'm going to say, okay, that's my ladder, and this is where my angle theta naught is happening. So then we see FG is acting straight downwards. So I'm going to draw in a line right here that is straight down. And we know stuff about triangles, so we know, well, if this is 90 degrees because it's intersecting straight down, then this is kind of like that complementary angle, I think is what it's called. So this is theta naught, this is some other angle, I'm just going to call it like phi. So we know that theta naught plus this phi have to equal 90 degrees. And then if we have this, it's not called a perpendicular bisector, I don't know what it's called. We have this line that is cutting through our triangle. We know that if this is phi, this has to be theta naught. Sorry, not that part. But if we then introduce this perpendicular, there we go, this perpendicular and this parallel side, then this phi plus this theta naught, because we have 90 degrees right here, this phi plus theta naught has to equal 90 degrees. So we know that this interior angle right here is theta naught. Then if I'm going to do a little bit of trig to solve for this FG perpendicular, I see that I have this FG perpendicular is adjacent, this is opposite. So I can use trig. I know I have adjacent and opposite, so that is cosine. So cosine of theta naught equals FG perpendicular over FG. We know we're using the cosine. We're kind of running out of time, so it's going to be mg cosine theta is our force, then L over 2 is that distance. So our answer is going to be D. Sorry for rushing, I just don't want to make this into 2 videos.